Positron Access Solutions is pleased to provide you this presentation that will let you understand how you can extend fiber gigabit services over existing legacy wiring in underserved brownfield MDUs. The demand for gigabit in brownfield MDUs is exploding. We all lived through the pandemic and realized that customers now expect a lot more upstream bandwidth than ever. And that is tied to how you offer gigabit bandwidth and services to reduce churn. If you achieve that combination, you end up in a triple win scenario. Win for the property owner, a win for you as the operator, and more importantly, a win for the subscriber. So do not forget about the services that you can enable over broadband gigabit services, such as managed Wi-Fi, security, smart buildings, and so on. And what's important also is that buildings enabled with gigabit see a massive uptick in the real estate value. And that has been proven with entities such as WireScore and Rove that prove that gigabit speeds are now becoming an essential demand from your subscribers. There are multiple challenges in deploying gigabit services in MDUs, especially in brownfield buildings, where the heavy construction, the complexity, the cost to bring fiber to the door is simply unmanageable and will break any valid business case. And that is not taking into account the disruption that you're causing to the building owners and their tenants. On top of that, in February 2022, the FCC changed the regulatory framework to allow more open access. What this means is that exclusive agreements that prevented other operators from sharing the existing wiring, whether telecom pairs or coaxial cabling, are now no longer allowed. So this has removed significant incentives for the broadband providers to install fiber, since they can no longer have exclusive access to that fiber for periods sometimes extending as far as 10 years. But both agreements are still feasible. So what you want to do is find a solution that will allow a very positive rate of return, higher than fiber to the door, and with minimum penetration rates. There are multiple technologies to extend fiber inside MDUs. The preferred one or ideal one would be fiber to the home with XGS-PON, where you can fully take advantage of the 10 gigabit symmetrical speed. The problem in MDUs is that the cost per door is very high, $600 to $800, and that you have to deploy every single door at once, no matter what the take rate will ultimately end up being. And that means that you are faced with a very long payback period. On the other hand, the cable operators are trying to use a quick fix known as DOCSIS 3.1 I-split that improves the upstream bandwidth, but still deliver much less than 100 megabits per subscriber. This is done at a low cost, very simple to do for these operators, and provides a quick payback period, but it still delivers much less than the required gigabit uplink speed. So DOCSIS 4 has been the answer. In theory, DOCSIS 4 will deliver 10 gigabit symmetrical speeds, the same as PON, but the cost is deemed to be high, and early proof of concept and trials have proven to be very expensive and rather complex to put in place, especially when remote PHY or remote MAC-PHY technologies are being used, as they require fiber very deep in the outside plant, much deeper than what has been done to date, and new CMTS. So that has a very long payback period also. So the best answer for brownfield MDUs is a technology known as G.hn. It offers gigabit speeds now, both upstream and downstream, and by 2024, we will see speeds up to 10 gigabits on coax and 5 gigabits on telephone pairs. The cost is much, much lower, about 20% of the cost of fiber to the home. And the complexity is very low because we just reuse the existing coax or telephone pairs. Obviously, it needs fiber in the outside plant, so it usually goes alongside with fiber deployments in a given neighborhood, but limits fiber to be at or near the building where it can be connected with GDHN to the existing legacy wiring, so therefore that provides the quickest payback of all of these technologies. G.hn is an ITU-T standard. Basically, it offers nominal rate of 2 gigabits per second per port, and it's part of a device known as a G.hn access multiplexer, or GAM, which is essentially a switch Ethernet that has overall 80 gigabits per second of switching capability. And G.hn has dynamic transmit allocation over both telephone pairs or coax to basically provide the best upstream and downstream performance with speed test at any point in time. And when G.hn is run over coaxial cabling, it can reuse the existing cable TV splitters to serve up to 16 subscribers or 16 doors per coax segment. So it installs and activates in hours and is extremely economical. And when running over telephone pairs, Positron has expanded the vector boost technology to provide even more robust operation when there is crosstalk with optimal spectrum management. The GAM is basically indoor or outdoor devices that are terminate fiber and then achieve gigabit speeds on copper to about 800 feet or 250 meters, and on coaxial cabling can achieve the same gigabit speeds at 2600 feet or 800 meters. So here we have examples of indoor and outdoor units, where the outdoor units are all extended temperature, IP68 weather resistant, and can be remotely power fed. With G.hn, we will see how we can convert bypassed doors, where ultimately the fiber is in front of the MDU but cannot be activated, to fully leveraging that existing fiber using G.hn technology in these buildings. The Broadband Forum defined a technology known as TR419 that basically defines fiber to the expansion point, or sometimes defined as the economical point, which is the closest point to the MDU where it makes sense to deploy fiber. As such, you avoid all of the in-building fiber infrastructure. Reusing the copper or coaxial infrastructure saves a lot of time and money and complexity, and still allows you to deliver gigabit speeds to your customers. So fiber extension up until now was termed as extracting the Ethernet frames from the fiber feed and delivering those Ethernet frames over the legacy wiring to each of the subscribers. But it is leaving out a critical element, which is the subscriber management. So what you want to make sure as fiber extension, you need to be able to define, activate, manage subscribers, bill for services, and also provide analytics, just the way you're doing it when you do fiber services to someone's living room. So fiber extension needs to be G.hn, the notion of fiber to the extension point, and OMCI integration. So how do we achieve that? First of all, from the OLT all the way to the GAM that is serving a MDU or MTU, the subscriber domain needs to be expanded natively exactly in the same fashion as when you feed a standard ONT. And then the GAM will apply those subscriber settings and deliver gigabit speeds by extending on coaxial phone line. So G.hn is definitely the optimal solution, especially when we look at coax. Normally with DOCSIS high split, the spectrum of 5 to 204 megahertz is used strictly for upstream bandwidth. That achieves about 1.5 gigabits per second, but shared over usually 100 plus subscribers, which explains why at best anyone can expect to achieve around 100 megabits per second in the upstream direction. And then after, there's a little bit of a gap between the spectrum. Channel 30 and above is used for regular cable TV and also for the downstream DOCSIS direction, which means that at higher frequency there is more attenuation and therefore the need for amplifiers. On the other hand, G.hn fully utilizes the spectrum between 5 and 200 megahertz, but doesn't use any spectrum above channel 30. So G.hn delivers 1.7 gigabit aggregate, which means that you can have gigabit speeds in both upstream or downstream in real time. But more importantly, 1.7 gigabit aggregate is serving 16 devices at a time, because the GAM is an Ethernet switch. So a 24 port GAM would be able to generate 24 gigabit of upstream bandwidth, which is a lot more than you can ever think of achieving with DOCSIS iSplit, and actually that exceeds the bandwidth that you would be able to achieve with the fully loaded 10 gig fiber, whether it is XGS-PON or 10 gig EPON. So GLHN also coexists with cable TV. So if you use the coax, some of your customers may want to retain their legacy cable TV. So the way this is achieved is a GAM takes the output from the cable TV feed amplifier, GLHN, using a regular 2-to-1 combiner. We now have GLHN and cable TV on the same coax. You insert a new splitter, a regular splitter, again, nothing special there. And each of the apartments, you take the wall plug, split it, one leg goes to an endpoint device such as the Positron G1002C+, that has 2 gigabit Ethernet port. One can serve the Wi-Fi router. The other port is available for future IPTV to the smart TV or set-top box. In this case here, we're showing that we have still legacy coax into the cable TV. What that does is allows us to have GLHN and cable TV on the same coax. For instance, that is very popular in hotel deployments, where we also need to preserve pay-per-view operation. So the GLHN can be notched to basically tell it start using the spectrum at 60 megahertz and above, and the spectrum below that is used for the pay-per-view control and other ancillary services that may be required. And even doing that, even taking away roughly 55 megahertz worth of spectrum, we still achieve gigabit speeds at about 1500 feet or 500 meters. So let's now focus on how we do the XGS-PON integration. So obviously, first thing you need is this XGS-PON SFP plus ONU. This is provided by Positron. It runs the standard function of an ONT along with some special software from Positron to extract the subscriber profile information out of the messages from the OLT and passing them on to the GAM so they can be enforced to each and every subscriber. A GAM is basically a core Ethernet switch, and it handles a fiber extension from the left using an SFP plus ONU and connecting the subscriber devices on the far right as gigabit ports from a GLHN endpoint, where it can be either a single device on the point-to-point configuration, mostly telephone pairs and occasionally on coax, or more likely point-to-multipoint, where we have up to 16 endpoint devices on the coax port. On a GAM, a subscriber is modeled first using a unique ID for the subscriber, telephone number, customer name, and optionally a bandwidth plan, where we can enforce bandwidth limits in both the upstream and downstream direction. And that is tied to a endpoint device, very much like XGS-PON as services identified to a ONT. And finally, the traffic for a specific subscriber is usually tagged with a VLAN. If we look at the OMCI managed elements, it starts with a physical path termination point, where each and every port of the GAM is mapped as a gigabit Ethernet UNI. So to the OLT, the GAM appears as a single optical UNI with a multitude of Ethernet ports attached to it. For each of these ports or subscribers, there's an optional bandwidth plan defined as traffic descriptors, and this is tied to a endpoint device or GLHN bridge, very much in the same way that an ONT is used to terminate a XGS-PON connection. Finally, the VLAN is used basically as per the MAC bridge port attributes for VLAN tagging and filter data that defines how VLAN tags are used and enforced. A GAM can enforce rate limiting in the downstream, but it's best to rely on the OLT to do this, since it sees the traffic before the GAM does. But in the upstream direction, the GAM can help enforce rate limits more efficiently because it sees the traffic first and then assist or help the OLT in doing this, although it does not replace the OLT being able to handle upstream traffic limitations. The way this is done is if we have again the GAM, looking from the right, every endpoint is mapped to a classifier as part of the Ethernet switch for each of the ports, and that classifier will do two things. It will enforce the bandwidth plan for each of the subscribers attached to these endpoints, whether it's over coax or telephone pairs. And then for the traffic that meets the bandwidth thresholds, it will look at the class of service and queue it in one of the 4 classes of services defined by XGS1 that happen to map the 4 classes of service identified by G.hn, and the scheduler for the uplink port will then interface with the ONU to push this data onward. It's much simpler. The GAM will receive all of the traffic, look at the VLAN or the inner tag, use that to identify the destination point, and then we'll enforce the class of services as per the PBit settings. And we'll do that for every port that then gets scheduled and transmitted to the endpoint and ultimately to the device attached to the endpoint. So in this case, we have 4 XGEM per subscriber, or 1 XGEM per class of service. Let's look quickly at some business case and real life applications. So typically when we have customers deploying this G.hn and OMCI integration, one is you reuse out of your existing backend. So a lot of cost savings and time to market simplified deployment because you don't have to do any IT integration work. Reusing the existing in-building wiring provides you a faster time to revenues, and the typical cost saving of using G.hn versus fiber to the door is at least 65 to 70%. We've seen cases as high as 80%. And all that without impacting the user experience. Everyone gets their gigabit services. So you can truly disrupt the market without being disruptive to the building itself. So if we look at how G.hn is more efficient than fiber to the door, and we've looked at the better or lower cost for fiber to the door at around $600. But what you have to realize that even with the high penetration rate or take rate of 45%, where normally everyone is happy with 25 to 30%, the effective cost per door goes way up to about $1,300. So if we take $1 million of CapEx, you could serve about 750 doors. On the other hand, if you do G.hn point-to-point, so typically over telephone lines, your average cost per door using list pricing from G.hn is about 325 doors. So $1 million of CapEx gives you 3,100 doors, so basically 4 times better than fiber to the door. And now if we do the same thing with coaxial splitters, where we serve about 6 to 8 doors per splitter, so we don't go the full maximum of 16, we basically see that the $1 million of CapEx will serve between 5,400 and 6,200 doors, so basically 7 to 8 times more efficient than fiber to the door. So some of our customers are really taking advantage of this. One of them is Novus in Vancouver, BC in Canada, where they're really covering the downtown metro area in Vancouver. Lots of high-rise buildings, fairly recent in many cases, but not easy to fiberize. And Novus relies on G.hn either over copper or coax, depending on the specifics of a building, to delight their customers with gigabit speeds very quickly and cost effectively. Another interesting project is with Project Waves. In this case, Project Wave is a non-profit organization, and their first rollout was in the Baltimore Olins House area, where they were able to very cost effectively leverage the government subsidies to delight 200 residents, mostly seniors and people with disabilities, with now gigabit access to the internet. They're now getting ready for expansion of their services in other areas in and around Baltimore, but they're also now being recognized as experts in this field and are being asked by other large metro areas to offer the same kind of services using the positron solution. As I mentioned before, the positron G.hn solution is also used in the hospitality market. An example is Marriott Hotels that we all know and love. Marriott is using older technology such as DOCSIS and VDSL 2 in 25 to 30% of their properties, seriously impacting their ability to deliver high-speed services and easy migration to IPTV. So we were able to save them significant cost savings analogous to what we do in the MDU space. So as we wrap up, GigaHN brings multiple technology benefits. It has native XGS-PON integration, so no IT work for the BSS, and the OSS will be simple to integrate. It's by far the most cost-effective gigabit solution in the MDU and MTU market, especially as we leverage coaxial cabling with the existing splitter technology, but also even on telephone pairs. So we get great gigabit speeds over distance at a fraction of the cost and complexity of any alternatives. It provides a very quick payback and therefore a much higher ROI. And it's given that it has a standard gigabit Ethernet output to the residential gateway. It's all compatible with whichever gateway you wish to use. And it's built over state-of-the-art Ethernet switch ASIC for carrier-grade services and capabilities and extensive management. GigaHN is therefore your ideal fiber extension technology. It operates very efficiently on coaxial telephone pairs. It has the seamless BSS integration and native XGS-PON and OMCI integration, much better bandwidth than alternatives, even technologies like MoCA and GFast. And we have even more sophisticated and powerful deployment operations such as daisy chaining for when your network needs to go beyond the reach of a single building. Thank you very much.